Okay, so let's continue on the computing the short time Fourier transform of cosine of omega naught t. We have found with this very nice general expression in which this depend upon the short time Fourier transform depend upon the Fourier transform of the window that we're going to use, and this is real, at least for the application that we are. If we use the box window, and the Fourier transform is exactly equal to the sinc function, which has zeros at n omega sub s, which is the frequency associated to the width of the window, so 2 pi over ts. And now we would like to see what is the effect of the width of the window on the Fourier transform, on the short time Fourier transform. And to do that, we consider let's plot the magnitude of this signal, of this Fourier transform. So let's compute xx of omega t, omega tau, amplitude squared, and this is equal to the x of s times the complex conjugate. Okay? Now the calculation here are pretty easy because since this is real, the window is real, we will have what? We will have the magnitude square of this part. So I'm gonna do it here. We have a quarter of w omega minus omega naught square plus the square of this. Well, the square of this times the complex conjugate of this. This cancel out. So we have w of omega plus omega naught squared. And then now we have to do the cross products because we have this term times the complex conjugate of this plus this times the complex conjugate of that. But when you do that, you will see that we're still going to get 1/4. And then I have this term times the complex conjugate of this. You will see that j omega and minus j omega cancel out, and then I get what I get, e to the j2 omega naught tau, and the double product of the two windows. Okay. And of course, then what I did, I basically did this times the complex conjugate of this, and we got this. But since this expression has to be real, of course, we will also have plus the complex conjugate of this other term, okay? Which is exactly what is given by this times the complex conjugate of this other term. And you see again that now you're going to get e to the minus j2 omega naught tau times this. So the final result is the following. So we have xs of omega tau squared is equal to 1/4 w of omega minus omega naught squared plus 1/4 omega square for the function omega plus omega naught. So actually I should be careful. So let's be precise. Square. And then of course, yeah, I can transform this in a cosine, and so I get 1/2 from 1/4, and so I'm going to get 1/2 cosine of omega naught tau times the double product of the two functions, of the two windows, the two Fourier transforms actually. Okay, so actually this is pretty general, and actually it's going to tell us a lot. Now let's remember that for a box, if the window is a simple rectangular box, this is the Fourier transform. W and now we're going to use it. So we can plug it inside here. And but actually maybe there is no need to plot it, so there is no need to to redo all the calculations again, or maybe we will do it. Let's see how it goes. Let me write this in a more elegant form, so I will try so to be more precise. I have a quarter W of omega minus omega naught squared plus a quarter of W omega plus omega naught squared plus a quarter, 1/2 cosine of omega naught tau times W, which multiply omega minus omega naught times W omega plus omega naught. Okay? So actually, yeah, from this expression we can learn a lot, because first we see that if and again, we have so we have W of omega, which is this. Okay. So let's plot. Let's try to plot it. Okay. In particular, you see that here we have a dependence on tau. Okay. But you will see that let's assume now at the beginning that the window is not large enough. The window is very large. Okay. So I'm gonna do the case that TS is very large. If TS is very large, the picture that you get is the following in Fourier in the physical domain. This is omega. Here we have 0. Here now we have omega naught. Here we have minus omega naught. Now you will see that the zeros of the window of the Fourier transform of the window of the sinc function are basically at the location omega n t sub s divided by 2 equal n pi. So we have that omega n is equal to 2 pi divided by ts times n. Okay, so it's basically n times omega sub s. Okay, if we call all of this omega sub s. And so what does it mean? It means that the zeros of this term, when I square it, will occur at the zeros will occur at omega n minus omega 0 equal n omega s. Okay? And the zeros of this guy will be at omega n plus omega naught equal n omega s. Of course, with n different than 0. So what does it mean? It means that, and now this omega s is equal to 2 pi over ts. So, as long as, so this is going to be minus omega naught plus 2 pi over ts, and this is going to be minus omega naught minus 2 pi over ts. So if ts is very large, if the window that we choose is very large, these two zeros will be very close to the origin, to minus omega naught. And here we have the same too, okay? So we have omega naught plus 2 pi over ts, and here we have omega naught minus 2 pi over ts. And of course, we also have to consider all the other zeros. Okay? So the amplitude here will be equal to a quarter of the value at omega naught, which is equivalent to is equal to the value at omega 0. So we have ts squared divided by 4, and then, it's gonna go down, and it will make zeros, and then dump out like a classical sinc function, okay? And here the same things, basically. So we have, the same values, and then it goes to 0, and then, and so on. Now, this is the case for a very large window. So what does it mean? It means that if this was our original signal, we chose a very large window. Okay? And you can see that we get good, when the window is very large, we get a very good localization in frequency, because we can clearly see the peak, all the energy is localized at the two frequency omega naught and minus omega naught, and that's what we would expect. And we also know that when Ts tend to infinity, when the window grows and grows and tend to infinity, then we know that this will tend to the delta functions. Is right, and that's what we expect. Okay, and what is interesting that this double term, this coupling term, doesn't contribute that much, because in this case Ts is very, very, very large, and then there is no the overlap is basically negligible. Okay, because when I do the product of these two functions, you see that they overlap in a regions where their values is very, very, very small. So what does it mean? It means that what I draw here is exactly the spectrum at any time tau, for any time tau. When the window is very large, for any this term doesn't contribute too much; it's negligible. Okay, and so at any time tau, when I move this window around, and the window is always very large, the short time Fourier transform always see the red spectra, the red spectrum. So you always see, more or less, always see the two frequencies, omega naught and minus omega naught. Okay, and that's what physically makes sense, right? If the window is large enough, wherever I move, I always see the main oscillations at plus minus omega naught. Okay, at any time tau. However, when Ts become very, very small, then what happens? Then they start to be a problem, because not a problem. Now the window is very short. Okay. So Ts is very, very, very small. Let's see what happens now. When Ts is very, very small, we will see that we see that now these zeros, since Ts is very small, 2 over pi over Ts become very, very large, and so the zero basically become wider apart, and so here. And the amplitude also reduces, because the amplitude is proportional to Ts squared divided by 4. So we get something. For example, we get something like this now, and the same things here. Okay. Now you see that there will be an overlapping region between the two functions here. They overlap. These two functions, they overlap. And now we cannot clearly see again, distinguish the two frequencies, okay? And now what's going to happen, that this term will be important, okay? And so at any time tau, this term will start to have some importance, and we will get different plots as we move around tau. So what does it mean? That as I move around the window here, I cannot recognize, since I have only a very short segment, I cannot tell, which frequency does it belong to, okay? And this is also depend upon where I am located around the on the x-axis. Okay. And here, no, I mean, we see for the first time, the effect of the the uncertainty principle, that if the window is very large, we're going to get good localization in frequency. But if the window is very short, we can tell now where we are in time, but we cannot tell exactly which frequency we see at that time, okay? So there is always we need to compromise. This is the famous uncertainty principle in quantum mechanics, for example. And so, to summarize, what we see here, that when we do the Fourier transform, if this is time and this is omega, what are we doing with the classical Fourier transform? We have an infinite window. So the infinite window, this is d omega tend to 0, but here delta t tend to infinity. So with the Fourier transform we have an infinite window. And so what does it mean? That we use all the information in time, but we lose all the information in time because we integrate over time, and we get the best resolution in frequency, because we get a continuum of frequencies. Because we need to have that delta t times delta omega has to be constant. Okay? So if the length is very long, if the resolution in time is very large, so we it's very we integrate over the entire time, the window is infinite, then we get the best resolution in frequency. However, with the short time Fourier transform, what happens is the following: is that when we choose a very short, a very long Fourier transform, a very long window, this is now delta t or ts, like we did it before, and this is delta omega. Now this area has to always be constant, okay? And so you see that now if the window is not infinite, we're gonna lose resolution in frequency. But this is basically with a long window. This is the STFT. You can even think this as a short time Fourier transform, infinite window. And instead, if you do a very small window, what's going to happen now is that the area is always constant. So now delta t is very, very small, and here delta t is very, very, very large. But delta omega become very large, basically. Okay? This is basically a short time Fourier transform with a short window. Okay? So, and as you saw before, as the window becomes shorter and shorter, we lose the resolution in frequency, and that's a problem. And instead, if the window is infinite, we get the best resolution in frequency, but that's going to be we get the Fourier transform. But we lose localization in time. And another example for this would be, let's try to do the chirp signal with but we need to choose